Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 16th lecture on the course Maritime Structures, Types, Construction, Pre-Service Analysis and Design. In this lecture, we are going to extend the discussion for materials used in maritime structures as a third lecture in this series. In this specific lecture, we will see the influence of carbon content in steel and influence of other alloying elements in manufacturing steel, how they affect the mechanical and structural properties of steel, weldability, ductility, toughness, Young's modulus, yield strength, tensile strength and etc. Let us see how these elements play a very important role in choosing steel grade for maritime application. In addition, we will also see the application of aluminum as a structural member material in maritime applications and the select area of applications where aluminum can be comfortably and confidently used in maritime applications. So, friends, welcome to the 16th lecture on carbon and alloying elements. Friends, there are three types of carbon steel as we designate from the literature: low carbon, medium carbon and high carbon steel. Each have significant variations in its properties. For example, if you want to nomenclate a steel based on the carbon content or carbon steel, it is generally indexed as, let us say, 10XX, where XX is the percentage of carbon content. For example, in steel grade 1006, one can say the percentage of carbon content by weight is 0.06%. Further, please note that carbon content higher than 0.3% decreases its weldability below a desired value. So, one may ask a question, what is and how to define weldability? How to compute weldability for a given grade of steel? We will do an example in this lecture, make you understand based on the chemical compositions and alloying elements present in steel, how to compute its weldability and then check the desirability of that for maritime application. Let us talk about different types of carbon steel as you see here. Let us say raw carbon steel has a carbon content varying from 0.05 to 0.3. It has a very high weldability and workability, but low hardenability, machinability, strength to weight ratio and wear resistance. So, low carbon steel though possesses high weldability and workability, but there are other issues related to this grade of steel. If you talk about medium carbon steel, the carbon content in this grade of steel varies from 0.3 to 0.6%. It has medium to low weldability. The weldability is slightly compromised compared to the low carbon steel, but it has a high medium surface hardening, strength to weight ratio and machinability. This particular grade of steel, which is medium carbon steel, has a specific application to crankshafts and couplings in electromechanical equipments which are used on top side of maritime structures. It though possesses low weldability, low machinability and workability, but has high hardenability, high strength to weight ratio and wear resistance. The common applications what we say in high carbon steel, which is about 0.6 to 1%, is on springs, alloying elements and cutting tools. So, friends, depending upon the grade of steel or especially the carbon content present in steel, its application varies because the structural properties of the steel significantly gets altered by just the presence of carbon as an alloying element in steel. So, we say low carbon, medium carbon and high carbon steel has specific applications. Okay. So, one cannot simply use steel for all components of maritime structures or all components are members of these structures. You have to be very careful in choosing them because their applicability is governed by also predominantly the carbon content present in the alloying element. Having said this, let us then ask a question, other than carbon, what are the rest of alloying elements present in steel and how they can affect the structural properties of steel. So, let us talk about different alloying elements and their influence on mechanical properties of steel. Talk about aluminum. Aluminum improves case hardening through nitriding, bismuth improves machinability, boron improves hardenability, chromium improves hardenability and corrosion resistance. So, chromium is a very desirable characteristic element or an alloying element present in steel for maritime application. Copper also helps to improve corrosion resistance. Lead improves machinability. Manganese reduces brittleness and removes excess oxygen and increase hardenability. Molybdenum improves toughness. Nickel improves toughness and corrosion resistance. Silicon improves strength. Sulfur improves machining. Titanium reduces martensic hardness in chromium steel. Tungsten increases melting point of steel and vanadium improves strength and ductility and also increases toughness at high temperatures. So, friends, various alloying elements as you see listed on the screen have different influence on the mechanical and structural properties of steel. So, steel, by choosing for its maritime application, one need to also pay attention to the percentage content of the alloying elements in addition to the percentage content of carbon, because this will govern the application of that steel for different choice of members in maritime structures. Let us now look at an important property of steel, which is weldability. What is weldability? Weldability is the ability of the steel to get connected to each other by welding. Okay? Weldability. Weldability of steel depends on alloying elements of steel. So, how to check weldability? So, weldability is assessed by calculating something called carbon equivalency. Carbon equivalency helps us to predict weldability of steel by combining the hardening effect of carbon and other alloying elements. Let us look at this equation. Carbon equivalency is given by the percentage of carbon by weight, manganese by 6, nickel and copper by 15, chromium, molybdenum and vanadium by 5. So, you can always compute carbon equivalency of any steel with known composition of alloying elements in percentage by weight. Substitute those values here, you will get equivalency. Once you have obtained the equivalency, based on this number, you can always say if this equivalency is up to 0.35, one can say the weldability is excellent. If this number is between 0.36 to 0.4, very good. If it is 0.4 to 0.45, good, and if it is over 0.5, the weldability is poor. So, weldability can be qualitatively assessed based on the quantitative estimate of carbon equivalency, which is dependent on carbon and equivalent content of other alloying elements in terms of carbon. That is why it is called carbon equivalency. Okay. Lower carbon efficiency equivalency means better weldability, one can see here. As the carbon equivalency keeps on increasing, weldability becomes from excellent to poor. So, lower carbon equivalency indicates higher and better weldability. Now, if you have a higher weldability or higher carbon content, what does it imply upon? Higher carbon content indicates a greater risk of cracking, okay, especially when they are provided in heat affected zones. Friends, in maritime structures, there are two important aspects which one need to ascertain. One is the temperature dependent property, because we have offshore structures temperatures varying from subsea temperature to very high temperature like 600, because we are using it for hydrocarbon exploration and processing. Furthermore, when you talk about coastal structures, the substructure are highly susceptible to corrosion, especially near the splash zone, as we saw in the previous lectures. So, we have got two important aspects of functional degradation in material. One is corrosion, other could be the temperature dependent properties of steel. So, one has to pay attention to both of these which is a very novel thinking process when you start using steel as a construction material for maritime structures. This choice and this depth knowledge was not required when you start using steel for conventional onshore structures. Okay. High carbon equivalency indicates tendency to harden and become brittle. So, carbon equivalency plays a very important role in understanding its application, weldability and choice to specific type of structures in maritime application. Iron carbon equivalency also makes the steel more susceptible to hydrogen induced cold cracking. Hydrogen induced cold cracking is one of the very serious problems we have in connections of tubular members or in connections of pipe joints and risers, which are very common in maritime applications in offshore structures. Therefore, friends, carbon equivalency, as we saw in this slide, helps to determine its weldability. It also checks whether we need a preheating to avoid weld defects. Okay. Sometimes weld defects can also be important part of degradation of connection strength. So, as you see in this case, if carbon equivalency is lesser than 0.4, steel possesses excellent weldability, preheating is not required. If carbon equivalency is between 0.4 and 0.6, as you see here, weldability decreases and preheating is recommended. If carbon equivalency exceeds 0.6, it is a very poor weldability and preheating must be done at this temperature before we use steel for connections. So, friends, depend upon the alloying elements, their percentage of composition by weight, carbon presence, we compute its weldability qualitatively based on the quantified values of equivalent carbon content present in the steel composite or element because of the alloying elements present in steel. So, now let us see how many institutions and how these institutions calibrate the weldability of a given steel. There are about 1, 2, 3, 4, 5 methods, 5 equations by which I can compute carbon equivalency. Once I know carbon equivalency, we now know how to compute or how to assess weldability based on this table, correct. If I know the carbon equivalency, qualitatively I will know how to assess its weldability. Now, the question comes, how do I compute carbon equivalency? International Institute of Welding IIW gives me carbon equivalency by this equation, which works out equivalency based on certain alloying elements which are dominant influencing the carbon content. One is manganese, nickel, copper, chromium, molybdenum, vanadium. Based on these percentages by weight, one can compute carbon equivalency. The other equation available in the literature is Japanese Welding Institute percentage carbon equivalency. So, carbon equivalency is again dependent on carbon plus silicon, copper, chromium, nickel, barium, vanadium and molybdenum in terms of their weight by percentage, and one can also compute carbon equivalency. The Durand carbon equivalency equation, which is used in French systems, is given by this composition. Thyssen is another institute which is given up an equation for carbon equivalency, and of course, commonly used Eurocode is also helping us to compute carbon equivalency based on the alloying elements composition present in steel. Now, one will get a very common doubt. There are 5 different equations available in the literature. What equation should I use for checking the carbon equivalency of the steel I am going to use for my maritime structure? First of all, why there are so many? It is very interesting question, friends. Initially, only IIW was recommended for computing carbon equivalency. Later on, as material science engineering expanded its horizon of knowledge, then many other institutes also start giving these equations of computing carbon equivalency. So, new developments include hydrogen susceptibility cracking and low carbon effects based on the advanced research conducted in material science engineering. Though there are 5 equations, which should I commonly use? The commonly used equation till today in maritime structure is IIW equation. However, if the carbon content by weight is lesser than 0.11%, okay, there is a point decimal here, lesser than, I will put the decimal here, it is better. If it is lesser than 0.11%, okay, then one can use the Japanese equation. So, most commonly friends, this International Institute of Welding equation recommended for carbon equivalency, but one can also sometimes use Japanese equation to compute this. I repeat again, once I know the alloying elements present in steel by percentage of weight, I can take their constituents, compute carbon equivalency from any of these equations. However, literature commonly refers this equation for carbon equivalency. Once I get the carbon equivalency, then I can go back to the state and qualitatively assess the weldability of that particular steel. Okay? Obviously, we all know weldability should be either very good or excellent to be used in maritime structures, because we are using connections which are probably welded together. We do not use bolted or riveted connections in maritime structures at all. Okay? Okay. Having understood this, let us see also slightly what would be the influence of temperature on important characteristics of steel like Young's modulus and yield strength. Though we will discuss about this in detail in some other course later, or there are good references available to you in the SwayamPrabha website, because temperature dependence properties are very interesting phenomena of research which has been established by various researchers in the world. So, there are good references cited in the SwayamPrabha course listing. So, please have a look at them for additional reading. For our knowledge sake, I have just extracted 2 of these curves from the website. Okay. The temperature dependence of Young's modulus and yield strength. One can see very well here, as the temperature increases, I am talking about the service temperature. As the temperature increases, Young's modulus decreases, and practically at about 1200 degrees Celsius, it practically becomes 0. Steel becomes completely flowable, totally flexible, no stiffness at all, and therefore no Young's modulus at all. Okay. Similarly, till about 400, there is no variation in yield strength for steel, but the moment the temperature rises from 400, it significantly reduces within about 400 degrees Celsius. Okay. So, up to 400 no issue, from 400 to 800 it is significantly decreases, and above 800 the steel becomes completely useless. Okay. The Young's modulus is very. So, these are reduction factors, as you see in the screen. So, whatever Young's modulus and yield strength value you have for steel, multiply this with this factor to design that particular element for higher temperatures. Okay, that is a very simple approach which I am suggesting for you to use, and of course, they have good references which are listed in different literature available in the international standards. Having said this, let us also see how temperature influences specific heat of steel and how temperature influences thermal conductivity of steel. So, these are very important segments of understanding and interest, because you know steel property significantly varies, significantly degrades at higher temperature, especially when you are using them for topside, where the exploration and processing happens at a very high temperature. Then the temperature dependence of properties should be accounted in the design, otherwise the design will have a faulty approach or a faulty result. Okay. We will now move on to Another important aspect of element or the member or material for offshore structures or maritime structures as aluminium. Aluminium so far for a long period have not been used for structural applications. They have been used for cladding, partitioning, non-load bearing elements, etc. In recent times, friends, aluminium has also geared up to become a structural element member, and in offshore systems they are prominently used on different locations. But remember, even steel with percentage of carbon and weldability and composition, all grades of steel cannot be used for all structural members. We have seen that. Okay. Similarly, aluminium cannot be used for all applications of members in maritime structures. There are specific areas where aluminium can be used. However, aluminium is now acceptable element or member or material for offshore structures and maritime structures. Aluminium, friends, is equally strong, malleable and low density metal. The advantage is when you use aluminium in the superstructure or anywhere admissible as per the codes, the weight significantly reduces. We all know the weight or mass is a very important contribution of payload aspect in offshore structures, especially when you talk about floating structures. We already said that in number of lectures earlier. Form dominant design always compromises on weight, reduces the weight, increases its floatability and tries to make the structure flexible, and the structure responds to the loads only by geometric form, not by strength essentially. So, weight reduction is a very important achievement in structural design of maritime structures. Here comes aluminium, whose weight or density is far lesser compared to steel. Okay. For example, steel has got a density 7850 kg per cubic meter. Okay. I would want you to guess what would be the density of aluminium. Okay. Will it be higher than steel? Probably it will not be higher than steel. It cannot be higher than 7850, that is okay, understood. So, what would be the ratio? Okay. Please look at the literature and try to explore what is the density of aluminum, but it is a very low density metal which can be used, and aluminum possesses very strong resistance to corrosion, and here it becomes a very interesting candidate for maritime applications, because we are always bothered about severe corrosion in maritime structures. Okay. Aluminum alloys are generally designated with 4 digits. The first digit specifies the principal alloying constituent, second digit specifies the variation of initial alloy, third and fourth shows individual alloy variation but have no significance. For example, if I have 1 XXX aluminum, it means it is pure aluminum, because the first digit specifies the principal alloying element and 1 refers to 99% contribution of aluminum. So, it is a pure aluminum. 2 XXX represents aluminum copper, 3 XXX represents aluminum manganese, 4 XXX represents aluminum silicon alloy, 5 XXX represents aluminum magnesium alloy, 6 XXX represents aluminum magnesium silicon alloy, 7 XXX show aluminum zinc alloy, 8 XXX show aluminum and other elements, and 9 XXX series is actually unused. So, friends, the first digit varying from 1 to 9 helps us to know the purity of aluminum and which can be used for maritime application. Okay. Aluminum is alloyed with different elements to improve its strength, ductility, formability, machinability or electric conductivity. These are all other special characteristics where aluminum is generally used as material of construction in maritime applications. Amongst all the aluminum alloys available in the market, the non-heat treatable aluminum magnesium alloy, which is actually the 5X series. Okay. The 5X series is aluminum magnesium alloy. This alloy is the one which is most suitable material for maritime application. So, if at all I look at aluminum choice for construction of maritime structures, I will always say let me use 5XXX series. Remember, this first digit contributes to the purity of aluminum present. 1 is 100% pure, 99%, and these are all alloying elements. Okay. Therefore, as the number keeps on increasing, the alloying constituents in aluminum keeps on increasing. So, 5XXX is a very common series used for maritime applications for aluminum. Now, as we saw in steel, aluminum also has temper designations. Let us see how. If I have a designation of F in aluminum, then I can say it is as fabricated. If I have designation O, it is annealed. If it is H1, H2, H3, it is strain hardened, and strain hardened annealed, strain hardened thermally stabilized. If I have W, solution heat treated. If we have T series, T1, T2, 3T, etc., it indicates cooled from elevated temperature for improving the shaping process. So, friends, designation is very important to understand the nomenclature of aluminum. Okay. Furthermore, let us look at the structural properties of aluminum alloy. We said they are comparable with steel. Let us for example take AA aluminum alloy 5083. We already now know 5 series represents aluminum magnesium alloy. Okay. 1 represents pure aluminum. So, 5XXX, okay, 5XXX, 5083 is one aluminum magnesium alloy which is being used, and let us see what is its yield strength and ultimate strength. Friends, look at this figure. Yield and ultimate strength are relatively comparable with steel, because you know steel has got yield strength of about 350 to 400 megapascal, whereas aluminum closely has about 250, not bad. So, we need not use it for major structural applications, but you cannot deny using aluminum as a structural element. And it also possesses equivalently good percentage elongation, showing good ductility. Okay. Of course, their properties decrease or they degrade with multi-pass welds. If you look at 6000 series, then they have higher yield and higher tensile strength. And furthermore, if you have got the property of temperature cooling, then they also have different significance in the yield strength and ultimate strength. So, friends, by designating aluminum with the first number and by saying aluminum with T series, we understand what is the nomenclature we are referring to and what metal we are actually referring to. Okay. Having said this, friends, let us say material selection therefore in maritime structures depends on classification of offshore structures. It is important to consider minimum expected service temperature to be used, because material properties varies with temperature. Structural element category and material thickness govern the selection. We already said that, because the yield strength and Young's modulus and other properties vary with thickness. This is a very interesting information. I am sure you will appreciate this, because this was not a conventional way of looking steel for structural design in land based structures, because thickness affects its strength. Therefore, material thickness also governs the choice of this material for structural construction. So, that divides this into special, primary and secondary applications. So, let us see what are the examples and how they are divided. Let us say special applications refers to structures under high stress. You can give some examples: joints, sections of high stress concentration where major failure is expected to happen. Primary applications refers to primary load carrying members where fracture could induce major structural failure. Secondary applications refers to less critical members due to combination of lower stress and favorable geometry. Their fracture may not cause major structural failure. So, structural elements in maritime structures and offshore structures are classified as secondary, primary and special elements, and based on these, then you can choose material for construction of these kind of members. Let us see some critical applications of special application members. Special application members are most critical members in maritime structures. They are examples of external shell or a deck element of an offshore structure. There can be also intersection of vertical columns can also be called as special elements. Examples could be a small portion of deck plating, heavy flanges, deep webs, etc. can be all under the category of special application. Their interaction with the major bracing elements make them as candidates of higher stress concentration. Therefore, they have critical joint nodes which need to be addressed very carefully, and therefore, apart from designing the joints, choice of material for creating the joints is also an important aspect in design of maritime structures, which is a very interesting information which you learn from this lecture. Let us talk about some applications on primary members. These members are referred as intermediate structures. Examples could be lattice legs, external shell plating of caissons, deck plating, main brace and jacket legs, heavy flanges and deep webs, and other members which require local reinforcement or continuity at intersections. Examples of secondary members could be the least critical members, bulkheads, girders in legs and columns. Deck plating is not essentially a secondary element. Low stressed members like deck beams, bracings can be also considered as secondary applications. Plating of certain columns to protect them from corrosion effect as well as to improve their slenderness effect to resist lateral or buckling loads, they can also be called as secondary application examples. Okay. So, friends, let us look at this table given by an international code. If we talk about application areas as special, primary and secondary, depending upon the service temperature, and depending upon the thickness, the values given outside are in millimeters, the values entered inside are in inches. Let us talk about millimeters. Look at the temperature varying from 0, 10, 20, 30, 40, 50, negative. Okay, I am talking about cryogenic, I am talking about negative temperatures. Different applications are possible, but if you talk about A grade steel or A grade material, then they can be used at different thickness at different temperatures. For example, if you want to use them at 0 degree Celsius, you can go with 30 mm thick. If you want to use them at minus 20, you should go for only 10 mm thick and so on. And only for secondary application, A grade cannot be used for special application, and A grade cannot be used at minus higher temperatures. So, this classification is quite interesting, recommended by international codes. Now, let us see what is A grade means. Open this code. If I say structural steel ASTM A13194 grade A. Okay. So, grades of steel are also classified as we saw in the previous lecture, which can be used. So, steel cannot be simply referred as a common term, as a loose term in design of maritime structures. Be very careful, the composition, the grading and the percentage alloying elements play a very important role in designating steel and using them for different applications at different temperatures and subgrade temperatures. Be very careful when you recommend or when you read the literature based on steel or aluminum used for maritime applications, friends. Okay. So, if you look at, for example, ASTM 13194 grade A steel, the yield strength is about 235 and the tensile strength is about 500, which we generally use for construction in land based structures as well. So, friends, there is a lot of grading available for different structures. Similarly, if you recollect, we have also grouped steel based on yield strength So, one can see group 1, group 2 and group 3 available in the literature. So, structures are constructed with steel. Steel is grouped and classified. The alloying constituents of steel plays a very major role in designating them and also identifying them for specific applications at specific temperatures in steel, and weldability governed by carbon equivalency given by 5 different institutions literature help us to assess qualitatively, can I weld this metal or not. If you cannot, then you can also improve its weldability by preheating it. So, now pre-processing of steel before it is to be used in maritime structure application is a very important knowledge, information we gain from this lecture. Now, I will do a simple summary before we proceed with a design example. Friends, material selection in maritime industry is governed by effective functionality of the structure. Steel is the most preferred material, no doubt about that, but equivalently aluminum and titanium are also used, though they are prohibitively expensive, but they are also used on certain applications. Codes, international design codes help us to classify steel in many ways. Friends, very importantly, strength is not the only governing criteria for design, remember that. So, never use a steel design in maritime structures based purely on its strength. It is also governed, it is also influenced by various parameters, by its alloying elements composition, by its thickness, okay, by its method of manufacturing, by its application nature, in what form of structure you are using, and so on. So, strength is not the only criteria which will govern the design. Weldability, formability, through thickness stress will also govern the design, friends. And when we talk about floating structures, in particular strength to weight ratio, which is a very usual check in design, does not apply to offshore structures. It is governed by strength and stiffness. Okay. Weldability governs material selection. Alloying elements confirm weldability and strength. Corrosion resistance, fatigue strength and fabricability are equally important. Maritime structures focus on prevention maintenance. Therefore, corrosion resistance becomes a very important aspect which is generally monitored by health monitoring of structures, which is mandatory. Maritime structures are repaired when they are loaded. So, one has got to be very careful in material selection, because material selection is also affected by service temperature. Charpy test results are also used in classifying materials. Or temperature dependent, alloying elements of steel behave differently at different temperatures. Strength, ductility and modulus of elasticity also degrades with temperature. We have seen this. Okay. So, friends, we will do a small example to understand the weldability. Let us say I have a design exercise here. There are 3 grades of steel: S sulfur, 355, grade 7, grade 1, grade 1. I have chosen 3 steel from the market, from the literature. Okay. Their chemical composition of alloying elements are given by weight. Okay. Carbon, silicon, manganese, phosphorus, sulfur, aluminum, titanium, copper, chromium, nickel, molybdenum, neodymium, vanadium, all these are given in percentage. Okay. What different grades of steel? What I want you to assess is, comment the few grades of steel. 1. Identify the group of steel. First, group them. Secondly, assess their weldability and hydrocracking susceptibility. Identify the critical yield and Young's modulus at 600 degrees. What happens to it? Okay. Then rank them for use of maritime structures. Okay. So, let us try to do this example. Let us say take this steel, carbon and all percentage are given. Let us first work out, or first let us group the steel. Okay. You know, steel is grouped based on the yield strength value. If you look at S355, this number indicates yield strength. Okay. So, yield strength of this is 355 megapascal, yield strength of this grade is 420, yield strength of this grade is 460. So, let us first find out this. So, I will do a sheet, I will say S 355 grade 1 has Fy as 355 Newton per mm square, S 420 G1, okay, G7, this is G7, sorry, this is G7, G1 has got Fy as 420 Newton per mm square, then S 460 G1 has Fy as 460 Newton per mm square. Please look back your notes and tell me they belong to which group. I can now say, looking at the literature which we explained in the last lecture, I can say this belongs to group 2 and these two steel belongs to group 3. Am I right? Based on the yield strength. Okay. Now, furthermore, let us compute the strength reduction of this steel grades at higher temperature. Okay. So, yield strength, let us work out yield strength factor and Young's modulus factor. Let us take the Young's modulus is 210 gigapascal. I will multiply this with the factor to compute the actual strength. Okay. And let us say the yield strength is 355 for the first grade, and again this is for the second grade 420, and for the third grade it is 420, and for the third grade it is 460. Let us try to work out these factors. For S 355 G7, S 420 G1, S 460 G1. Okay, these are the grades here. Look at this particular curve. Look at this curve. Young's modulus reduction. I am talking about 600 degree. Okay, I am talking about 600 degree. So, I draw a vertical line. Okay, I see the reduction is about 0.3 for Young's modulus, right. So, what I will do now, I will go back here, multiple reduction factor as 0.3 in all the cases. I should say 0.3. Okay, let me rub this line and mark it here. So, I say reduction is 0.3, all steel has the same behavior. So, I can now compute this value, okay, as 63 gigapascal GPa, 63 gigapascal. So, there is a significant reduction in this. Okay. Similarly, let us look at higher temperature, work out the yield strength. Look at this curve. Look at the yield strength part. Okay. At 600 degree, the yield strength is about, let us say, 0.45. So, multiply this with 0.45. 0.45, I will multiply this. So, 0.45, again 0.45 with the steel and this steel, I can get these values. Okay. For example, this is about 160 Newton per mm square. Friends, there is a degradation of yield and Young's modulus. You cannot use a standard number for the design, okay, when use it for higher temperature. Be very careful about that. Now, let us work out the carbon equivalency. Carbon equivalency I am going to do with this equation, silicon in percentage by 30 plus copper in percentage and chromium in percentage by 20 plus nickel in percentage by 60 plus barium by 5 plus vanadium by 10 plus molybdenum by 15. I am using equation given by Japan Weld Institute. Okay. If we substitute them for S355 grade 7 steel, I will get this as 0.14 plus 0.35 by 30 plus 0.3 plus 0.25 by 20 plus, look at the table, right, 0.5 by 60 plus 0.1 by 5 plus 0.06 by 10, 0.08 by 15. So, all these percentages of different alloying elements are available here, okay, are available here. So, I have chosen these values, substituted them. I am trying to find out what is the equivalency now. I get this equivalency as 0.218 carbon equivalency in percentage. Okay. Once I get this, I go back to this table qualitatively and tell is it weldable or not. So, I go back to this table and say 0.28 up to 0.35 I have got excellent weldability. So, now I can say S355 G7 steel has got excellent weldability. Okay. Friends, that is how we rank them and so choice of steel depends on various issues. Now, let us look at the summary of this lecture. In this lecture, we understood the material properties more in detail. We understood the alloying elements, okay, change, influence the properties. Thickness also matters, applications of these also matters at different temperatures. Then we generally use something called carbon equivalency to check its weldability, and there are different equations given by 5 institutes in the world and we can use any one of them depending upon that. So, choice of steel does not depend only on strength, but also on various parameters as far as maritime structures are concerned. I believe that this lecture has given you a different insight of using steel or aluminum as construction material for maritime structures. Thank you very much. Namaste.